Hey chemists, this video is about heat transfer and the use of Q equals MC delta T in really a calorimetry problem that heat in equals heat out. And on paper, we're going to assume perfect on paper. There's no heat loss to the surroundings on these problems. So when we have heat transfer, we are going to say that our warm object, our heat in, is going to equal our heat out. So our heat in is going to equal the release of the heat out of the hot object. So heat in is going to heat out. That's going to be our heat transfer big idea. So I'm actually going to start this lecture with number 5. And number 5 and below it, number 6, are really similar to your specific heat of a metal lab that you guys are going to do. So we're going to practice these first, and then we'll move around. We'll go back to number 1 on this worksheet. But starting with number 5, we know a 25-gram aluminum object is placed in a warm oven for several minutes and then is transferred quickly to a calorimeter, or your styrofoam cup, of water at 37 degrees Celsius. Specific heat of aluminum they provide us at 0.90 joules of energy to raise 1 gram of aluminum 1 degree Celsius. Our final temperature of the water, which has the aluminum in it, so it's also the final temperature of the water, is 39 degrees Celsius. We want the mass of the water in the calorimeter. So again, our big idea is the heat into the cold object is going to equal, in a perfect lab, perfect on paper situation, the heat out of the hot object. So every time we do one of these problems, we're going to have two Q equals MC delta T algebraic equations. We'll have enough information to solve for energy of one of them, and then we can solve for joules, flip the sign, which I will show you in this video, and then we'll go through and solve for the information on the other side. Step by step, just stick with me and you guys are going to do great. Okay, so in this problem, what do we know enough about? Do we know enough about the hot aluminum? Let's see, Q equals, we know the mass. We know the temperature initial of the aluminum. We know the temperature final of the aluminum because it's going to be with the water down here. And we know the specific heat. So we know lots about the aluminum. So first, let's find out about our hot aluminum. We're going to find the energy there. So our energy of our aluminum. We have enough information quantitatively to figure this out. So we're going to have the mass of the aluminum. We're going to need the specific heat of the aluminum, and we're going to need the delta T of the aluminum. All right, so mass of the aluminum we know is 25.00 grams. We know the specific heat of aluminum is 0.90 joules per gram degree Celsius. And we know the delta T of the aluminum. So delta T is T final minus T initial. The final temperature of the water, which the hot aluminum gets placed into, is 39 degrees Celsius. 39 degrees Celsius. And the aluminum started out in a hot oven, 80 degrees Celsius. The hot aluminum is giving energy. So we are releasing energy from the hot aluminum. So it makes sense that my delta T will be a negative temperature value, which will reflect in a negative temperature value of the aluminum. So let's see, I do 25 times 0.90 times, in parentheses, 39 minus 80 degrees Celsius. I end up, and I'm not going to run sig figs right now, but I end up with my negative 922.5 joules. and that is going to be my energy of my aluminum. I know it's kind of flipped here, but now that I know my energy of aluminum being released, I can say that is equal to the energy absorbed of the water, but I quantitatively flip the sign. That's the energy of my water that's being absorbed. That's the energy that's going into the cold water. All right, now that I know that I have my heat transfer step done, I can determine the mass of the water in the calorimeter. I didn't know that, but now I can figure that out. So here's my hot aluminum. Here's my heat transfer. Now I can find my mass of my water. So next step, I'm going to have all my water calculations. So I'm going to need a Q of water, which I have right here. My mass of water, what I'm trying to figure out, I don't know that, that's going to be my X value. My specific heat of water, good thing I've got that one memorized. If not, it's on the previous page. And then I'll have my delta T for water. So I know my energy of water because I flipped my sign. The energy from the water came from the aluminum losing all its energy to the cold water. So I know this is 922.5 joules of energy. I don't know my mass of water. You can put X there. I'm going to put M sub W. I know my specific heat of water is 4.18 joules per gram degree Celsius. If you want to use 4.184 joules per gram degree Celsius, that's okay too. I'm dropping that final 4 because that's what it gave me on the previous page. All right, now I got to be careful with my delta T of water. My T final, because the aluminum gets placed into the cold water, the T final isn't the same for both substances. Just like your T final was the same in your Find That Heat While Cool lab for hot and cold water. T final is the same for the hot aluminum and the cold water. All right, T initial, the cold water was colder than the final temperature. So I've got 37 degrees Celsius here. All right, I'm going to have to subtract, multiply through, and then divide each side by whatever that comes out to be. And my mass of water after my algebra ends up being rounded to sig figs because I need 3. Your delta T gives you sig figs, 1, 2, 3, 1, 2, 3, 3 sig figs, 110 decimal, just like it matches up here, and it's mass. That's why I sometimes keep the X off, because mass helps me remember what unit I need. If I just have the M, I know it's grams. If it's an X, I got to go back and figure out what was I solving for again. But 3 sig figs after my algebra is 110 grams. So all of these problems are going to be about heat in equals heat out. You'll know information, in this case, about the hot water. Then you'll have a heat transfer step where the heat out, in this case, what comes first equals the heat in to the cold water. And then the third step is going to be your cold water calculations. Or I could ask for the mass, I could ask for a temperature initial, I could ask for a temperature final, I can ask for a delta T. But in this third step, I could even ask for a specific heat if it wasn't water. Something in this third step you'll be solving for. All right. Go through this video again if it helps you, or go through, see if you can use this process, 3-step process. It will help you with number 4 is going to be that similar 3-step process, and so will number 2 and 3. The first problem on this page, the last problem on this page, is going to be used a little bit different of a technique because T final is the same. But this is going to be the place where we start.